Alright folks, so I'm creating this video in order to give an example here of applying Newton's laws for tangential and rotational motion for a rigid body where the motion is kind of in the plane. So in this example here, this beam, right, imagine this beam supported by two ropes, and the beam, I just made up some numbers here, are 4 meters long and 20 kilogram beam. And in equilibrium here, if we were to draw a free body, we would have two forces. We'd have a tension on the right, which is acting up, a tension on the left that's acting up, and an mg down. If this problem were static, it'd be pretty easy to show that those two tensions would be equal in length, and each one equal to half the weight. Right? Now imagine that this rope breaks right over here somewhere. Right? Now, when that occurs, the tension on the left-hand side goes away. So the free body now looks something like this. Okay? We have a gravitational force down at G, center of mass, or the center of gravity. Then we still have a tension up. Now in this case, by observation, I know that this mass is now accelerating down. The center of gravity is definitely going to accelerate down. So the mg would be longer than the tension. I probably should shorten that up a little bit, but I think I'll leave it. Right? And this is it. This rope is the only thing in contact with this beam. So when we go through and do the free body here, the gravitational force is a field force, no contact required for that, but most other forces, unless you're talking about electric or magnetic fields, require contact. So the tension is the only force. So the only other force acting besides gravity. So this picture that I'm kind of circling here, this represents the completed free body for the beam. Okay, now, the kinetic side of things. There's really three different types of acceleration to consider. Right? So here's G, the centroid. Conceivably, this could accelerate in the x or y direction. So in the kinetic picture, we're going to have an max, conceivably an may, right? And in addition to that, this thing is also going to start rotating, and the rate of rotation is going to be increasing. So there's really three acceleration terms we have to get over here: an max, an may, and an I alpha term for the rotation. Now, this I here I drew about G, so this I would be the moment of inertia of the beam about its centroid. So here's the free body showing all the forces. Here's the free body showing all the MA terms, or the I alpha terms. Right? Now, the next step is to start writing equations. So a quick, easy one, probably the easiest equation to write for this is sum of all forces x direction equals MA in the x direction, right positive. So I take a look at my free body here, right here. I don't see any forces in the x direction. Equals, right-hand side, only thing pointing in the x direction is ma sub x, and this equation pretty clearly tells me that at this instant in time, the acceleration in the x direction is 0. Alright, so, just had to check, thought I heard somebody knocking at the door. Alright, the other thing we can do here now is we can write another force equation. Sum of all forces in the y direction equals ma in the y direction. My standard rule of thumb for this is to identify the acceleration direction, call that positive. Right? So over here I've got ay pointing down, so when I write this equation, I'm going to call down positive. And then what we're going to have is mg minus t equals may. Right? So there's a second equation, a force equation we can draw for, or we can write for this free body. Don't need that. Alright. Now, as I look at this problem here, the thing to note, we know that the acceleration in the x direction is 0. That one, done, we don't need to worry about. The problem still really has three unknowns, though. We don't know the tension, we don't know ay, and we don't know alpha, the angular acceleration. Now, the I, the moment of inertia, this is no problem. Moment of inertia of a mass about, or of a bar about its center is 1/12 ml squared. We can either look that up or calculate it by direct integration. The point is that we still need to write some more equations here. I still have AY, alpha, and T. And we really only have one equation to work with. So we got to write two more equations. So the next one we're going to write is going to be a moment equation. And I really have a choice here. We could sum moments about G, or maybe about this right end, maybe about this point, both of which are perfectly valid. I'm going to go ahead and sum moments about G. So sum of all moments about G equals I alpha, counterclockwise positive. So summing moments about G is only going to yield one term because the gravitational force, its line of action goes right through G. There's no moment arm. So we're going to have T times R, and that moment term would be positive because this force right here, the tension, makes this beam want to rotate counterclockwise about G, and counterclockwise is what I call positive. Right? And the right-hand side equals I alpha. Right? So now what we have here is we really have two equations to work with. We got 1, 2, and we still have three unknowns: the tension, the AY, and the alpha. So we got to write another equation. We have exhausted all of our Newton's second law equations, though. We've written two force and one moment equation. We can write a different moment equation, like I could come over here and write a moment equation about this point right here, but it doesn't actually, it yields an equivalent equation. It doesn't yield an independent equation. So the next equation we're going to write here is going to be a kinematic type of equation. So I'm going to take a moment and get rid of a few things and clean it up, and then we'll talk about how to finish this. Alright, so I've gotten rid of, made myself some room here, gotten rid of some stuff. I stored these equations over here on the left. We're going to need these here. So we got equation 1, equation 2. Now, I've also put a little subscript here to mark this point. This point on the picture now I'm calling point R, and R because it's the right end. And what I'm going to do now is write a kinematic equation relating points G and R. Right? So, the acceleration of point G, all right, has to equal the acceleration of point R plus the acceleration of G with respect to R. Now, the acceleration of point G is what I'm calling this AY here. And that's in the, I'm going to go ahead and write this, that's in the minus J direction. All right. Now, the acceleration of point R has to be 0, and here's why. It is still connected to this rope here. So unless this rope breaks or gets longer, that point is not moving vertically. So AY at point R has to be 0. Right? Furthermore, we just showed that AX was 0 by the force diagram. Right? And also, there can be no centripetal accelerations because this thing is not rotating yet. So there's no acceleration. Acceleration R at the instant shown is 0. Okay? Acceleration G with respect to R can be written as alpha cross R G with respect to R. So this is going to be alpha k hat, where alpha is the angular acceleration, times R, that's G with respect to R. Now that's going to be, let's see, L over 2 in the minus I direction. Right? So this left-hand side now we got A sub y times minus J equals, this right-hand side can be written alpha L over 2, and then the direction is K, forgot my cross there, K cross minus I hat. So in a standard XYZ coming right at us, K cross minus I hat is minus J. And by comparing coefficients here, all right, now I have my third equation that I need to solve this. The relationship between AY and alpha is AY is equal to L over 2 times alpha. Right? So now what we have is three equations, three unknowns. I'm going to pause this again and get rid of a few things. Alright, I'm back. Done a couple little algebra moves here that I want to talk about. So, alright, so this equation, mg minus t equals may, I just recopied that right here. Alright, and then this equation, alright, t times r, that was coming from the torque produced about point G. The R would be this distance, which would be half the length of the beam. So that became a T times L over 2, right, equals. The I is the moment of inertia of a beam with an axis through its center. That's 1/12 ml squared. You can either get that by integration of r squared dm from minus L over 2 to plus L over 2, or just look it up. And then the alpha can be replaced with 2a sub y over L. So what we have now, oops, let's see, I don't need this. So what we have now are these two equations, two unknowns. And what I'm going to do here is I think I'll take this one and solve it for t. So t is going to equal, alright, so let's talk about the L's here. There's one of them here. There's effectively one on the right, so the L's basically are gone. And then on the right we got 2 over 12, that's 1 over 6, and then we're going to have to multiply that by 2, I think that's 1 over 3 now. So we got 1/3 m and a sub y. I think I'm going to take a moment and pause this and just double check my arithmetic on that. I think it looks good. So now I'm going to take that tension here and sub it into the equation above. This is now going to read mg minus t equals, whoops, the whole point of that was to get rid of the t. mg minus 1/3 m a sub y is equal to m a sub y. Now I'll notice these masses divide out, so now g is going to equal, and I would add this to the right, so we're adding a sub y to 1/3 a sub y, that's 4/3 a sub y. So if we solve this for a sub y, we get 3/4 g. Alright, now that would be 3/4 of 9.8 meter per second squared, or 3/4 of 32 feet per second squared. The next move now would be to take this a sub y, we could sub it in here to get the tension. The next move is we could take, after that we could take that a sub y, sub it here to get alpha. I'm going to go ahead and just end this video here. That problem's pretty well done. I'll leave that for an exercise to the reader.